Hey guys, welcome to the electromotive force, the next in our little study of circuits and current here. We've referenced it before, now we're gonna try to figure out a little bit more what it is, this electromotive force. So we know that when a battery is a source of potential difference, or the voltage, or electric energy. It's not really a force, right? When not connected to a circuit, there is a potential difference between the terminals. So we have our 9-volt battery, remember, and it has a negative and a positive side on it. So there is a potential between that. This voltage is also known as the electromotive force. Or the EMF, and we use the symbol epsilon, capital epsilon, to indicate that. So despite the name, this is a potential, not an actual force. This is back when we thought they were equivalent. So before we really knew how things worked, we started calling things and certain names, and we just kind of kept it. So that's kind of interesting. So for example, a car battery has an EMF of 12 volts. That's the big battery that powers your car when you start it up. But like a little lithium battery or like a AA battery that we use in a lot of our devices, or even AAA, has an EMF of 1.5 volts. As soon as you connect the battery to a circuit and current flows, the current that actually flows is always going to be less than the EMF, or epsilon for this. Because of this, there's an internal voltage drop. And the terminal voltage is always less than the EMF of the battery. So that's kind of the quick background behind it. There's a bit of Ohm's law that we have to use, but the equation is pretty straightforward. So we have this. We have the terminal voltage, or the EMF for this, is going to be the electromotive force minus I times R, where E is the EMF, the V term is the terminal voltage, and the R is the internal resistance of the battery. So those are the variables we're looking at. Note the IR in this little equation is the internal voltage drop. And if the battery is not connected to a circuit, there's simply no current, which means the terminal voltage is what the EMF of the battery is. All right, so let's take a look at a quick little diagram here that shows kind of how this works. Change my color of pen here. Okay, and so here's how a battery behaves in terms of the schematic. So here's that voltage source that we look at, and this is going to be the resistor that's hooked up to it. And then we have this other resistor that behaves like this over here. How we want to think about this is there's an external resistance R. That's going to be this battery over here. I'm going to have an internal resistance, little r, and then my EMF is going to be here. So this is going to represent the little r here, and this is the EMF. This part right here represents the battery. So we have the battery connected to something else, just like a normal resistor. But the battery, just kind of based on how it's made, has its own internal resistance. So when a battery goes dead, it's because the internal resistance builds up until the internal voltage drop matches the EMF. And so that's essentially, it runs out of juice, or it runs out of internal energy to where when the voltages start adding up, when they start matching up, the battery no longer has a potential difference, and therefore current can no longer flow. So a quick example on how we do some of these questions. These questions behave a lot like this. I have a 12-volt battery with an internal resistance. What is the terminal voltage of the battery? And so what's the first thing we look at is the equation. So the V terminal, let me change this to this guy here, equals epsilon minus IR. And it gave me that 12 volts is the electromotive force, or the EMF. That's what that is right there. We have a current of 3 amps, and then we have that internal resistance, little r, that's this guy right here. So I'm just gonna plug in underneath it. I think we're okay with that. There's my 12 volts. Here's my 3 amps. And my internal resistance of 0.22 ohms. So the terminal voltage that reads out, basically, is about 11.3 volts. So that's how the battery, while it's a 12-volt battery, it doesn't always spit out 12 volts simply because of how the battery works inside. So that's how that works in that case. So what about when you recharge a battery? So a rechargeable battery is being charged, an external voltage is applied to the battery in order to force electrons back into the battery. The external voltage must be greater than the battery's electromotive force. So essentially, the backwards that happens, so in fact, the external voltage must be, so here's my V terminal, equals the electromotive force plus IR, the internal resistance of the battery. And so a question like that sounds something like this. We have a 12-volt battery being charged by an alternator or something else that can supply 15 volts. And so most internal combustion engines have this set up. If the internal resistance to the battery is 1.3 ohms, what is the current through the battery? So we use the same idea, but backwards, electromotive force plus IR. So in this setup, we have to make sure we understand where the things are coming from. So I'm going to write this out real quick. So in this question, my epsilon is 12 volts. That is the battery. That terminal voltage, that's that external thing charging it. That's going to be 15 volts. And then the internal resistance, that has stayed the same at 1.3 ohms. So when I plug this in, I'm going to solve for I first. So it'll look something like this. I equals the terminal voltage minus epsilon over resistance. When I plug everything in, I get 15 minus 12 over 1.3, which gets a current of 2.3 amps running through the battery to charge it. And so in a nutshell, that's how the electromotive force works. Our study of circuits would be incomplete if we did not include this. So lots of questions will now include the internal resistance and the EMF of batteries. So good luck with your problem sets. Let me know if you have any questions. Thanks for watching. Bye.